Students. Continuing our lectures on the nano electronics, and we were discussing nano antennas in our previous classes. We have discussed about the basics of nano antenna and the bow tie nano antenna. Now, today we will discuss about something called bullseye nano antenna. So it looks something like concentric rings, like this, under the microscope, and it has got a single sub-wavelength aperture. So this is the single sub-wavelength aperture and surrounded by periodic surface corrugation. Surrounded by periodic surface corrugation. Now this concentric ring pattern was milled into a sapphire substrate. Milled into sapphire substrate, and which was then overcoated with 300 overcoated with a 300 nanometer silver film, and then was fabricated at the center, and a 200 nanometer diameter aperture was fabricated at the center. So first milling of the sapphire substrate, followed by a 300 nanometer silver film, and then aperture at the center of diameter 200 nanometer. This is the construction of the bullseye nano antenna. Now this bullseye nano antenna, creates a region of high electric field. So this is the shape. So it creates a region of high electric field at the center. Electric field at the center when light is incident at the resonant wavelength. what happens next is a portion of the concentrated field evanescently couples with the aperture and radiates into the far field. Mm. A portion of the concentrated field evanescently couples through the aperture and radiates into the far field. Now, if you look into the transmission spectra of such bullseye antenna, this is the transmission unit, and this is 0.25, and this is the wavelength lambda. In nanometers, and from 600 to 900 is the range. Then it shows a plot like this. And now, secondly, concentrate again on the traces on the structure of the bullseye antenna. I can find that there's some these traces. They correspond to measurements obtained using a white light source. Due to measurements using a white light source. And wavelength of the peak optical transmission, that means we're talking about this wavelength. Wavelength of the peak optical transmission, it's called lambda peak. Is determined by or rather we can say is a function of the groove periodicity. That means we're talking about these grooves. How periodic are these grooves? And also is a function of the refractive index seen by the surface class 1 wave. Refractive index seen by the surface class 1 wave. mediates the transmission. Now, the geometry of the correlation is on the backside of the structure and it greatly affects the near field and far field. So geometry is also important. Now, apart from this bullseye antenna, we can have antennas in terms of periodic arrays. Now, these periodic arrays can be periodic arrays means like this. Now, these periodic arrays can be of gold nanodots, elliptical gold nanodots. Of size 57 nanometers to 105 nanometers on an average, and call 60 to 100 nanometers, and it can be also due to metallic nanometers, nano apertures in solid. Metallic nano apertures in solid, in gold, and spacing between these is 1 micrometer lattice spacing. Now, the incident light at a frequency which excites the surface plasmon, at a frequency which excites the surface plasmon, enhances the electric field in the aperture. This is the one which will enhance the electric field in the aperture. And the molecules located within the nanosphere experience an enhanced optical excitations. So what it will do, it will molecules within nanosphere have enhanced and will go to an optical excitation, and also enhanced fluorescence. And due to this, what we can do, we can isolate the signal coming from the molecule inside the center than from the molecule which is outside the nanosphere. So it helps in isolating signals from molecules inside the nanosphere from molecules outside.